Lecture number 14, combined cycle, and combined cycle we will be doing problem number 9.93 from Moran and Shapiro. Helium is used in a combined cycle power plant as a working fluid in a simple closed gas turbine serving as a topping cycle for a vapor power cycle. A nuclear reactor is a source of energy input to the helium. Figure 9.93 providing the steady state operating data. Helium entered the compressor of the gas turbine at 200 pound per square inch, 180 degree Fahrenheit with a mass flow rate of 8 into 10 to the power 5 pound per hour and is compressed to 800 pound per square inch. The isentropic efficiency of the compressor is 80%. The helium then passes through a reactor with a negligible decrease in the pressure, exiting at 1400 degree Fahrenheit. Next, the helium expands through a turbine, which has isentropic efficiency of 80%, to a pressure of 200 pound per square inch, which means like the input pressure, which was P1, we are back to the exit pressure of the turbine P4. The helium then passes through an interconnecting heat exchanger, a separate stream of a liquid water enter the heat exchanger and exit as saturated vapor at 1200 pound per square inch. The vapor is superheated before entering into the turbine at 800 degree Fahrenheit, 1200 pound per square inch. So we have got a supplementary firing and that raised the temperature to 800 degree Fahrenheit while the pressure remained constant. The steam expands through the turbine to 1 pound square inch, uh, which is the input pressure of the condenser as well, and exit of the condenser. The quality of the steam exiting the turbine is 0.9. Saturated liquid exit the condenser at 1 pound per square inch, which is same as the exit of the turbine. Cooling water passing through the condenser experience a temperature rise from 60 degree Fahrenheit to 90 degree Fahrenheit. The isentropic efficiency of pump is 100%. Stray heat transfer, kinetic energy, and potential energy effect can be neglected. Finding the mass flow rate of the steam and cooling water in pound per hour, the net power developed by the gas turbine and vapor cycle, and the thermal efficiency of the combined cycle. So first thing first, what you have to do in this kind of example, like you have to draw the schematic diagram. Although the TS diagram would be a little bit difficult to draw, so it would be advisable to draw the schematic diagram before you solve the question. In schematic diagram, you just write whatever the condition are given um, on the both of the cycle. So we have got the topping cycle, which is the helium cycle, and that helium cycle is operating in with the help of nuclear reactor, which mean like we have already discussed in our previous lecture. So input of the turbine, input of the helium is 200 pound per square inch, temperature 180 degree Fahrenheit, and mass flow rate is 8 into 10 to the power 5 pound per hour. We do not know the temperature exiting the compressor T2, while we definitely know the pressure, which is 800 pound per square inch. The pressure would remain constant from state 2 to state 3 as we are entering the combustion chamber, or what we over here we have got the nuclear reactor, so we do not expect any um, change in a pressure when we are supplying heat to the helium. So pressure at 2, which is 800 pound per square inch, would remain pressure at 3, 800 pound per square inch, while the temperature rise from T2 to T3, which is actually 1400 degree Fahrenheit. Now expanding in a turbine, when we are expanding in a turbine, so efficiency of the turbine is 80%, while the pressure, definitely exit pressure of the turbine, which is written as 200 pound per square inch, which is same as P1, which was the inlet of the compressor. So we are back to the pressure, initial pressure, while the temperature T4 is not given over here. Similarly, for the Rankine cycle, which is the bottoming cycle, we have got the condition at the inlet exit of the HRB heat exchanger, or what we call it as a waste heat recovery boiler. Uh, the saturated, we are exiting at saturated vapor and a temperature and a pressure of 1200 pound per square inch. Then we raise the, although the temperature at T5 over here is not given. Um, we have got supplementary firing, and the supplementary firing raised the temperature of the steam to 800 degree Fahrenheit while the pressure remain constant. We might expect like whatever the saturation condition is, whatever the saturation temperature is, sorry, we do know the temperature over here, and that would be desaturated at 1200 pound per square inch. So whatever the condition over here is, it will be having a temperature rise, and the temperature rise mean like we would be having, I think, superheated steam over here. Then we are expanding in a turbine, and at the turbine we are exiting at a pressure of 1 psi and a quality of 0.9. Then we are entering into the condenser. Exit of the condenser would be same as 1 psi, as there is no pressure change in a heat exchanger, and we are assuming like we will be moving out as a saturated liquid. Then we are also being given the temperature of inlet of the cooling water and exit of the cooling water. So solving the question would require like different methods. One of the method would be like if you have got the helium table, you would be using that helium table at correspondingly temperature and pressure, and obviously you would be finding the enthalpy corresponding to that condition. But if you do not have got the helium table available, you can simply use the ideal gas equation, and from the ideal gas equation, you can find two of the condition. The other condition are known anyway, like the state 1 is totally known, state 2, state 3 is totally known, got a pressure and temperature. So we can find the enthalpy as well, which mean like delta H would be equal to Cp delta T. We would need the Cp value of helium, which is 5 by 2 R. We will discuss this later on. So that means we are only left with two of the condition at state 2, and let's say state and we have got at state 4. So state 2 can be simply find out by moving from state 1 to state 2. So when I'm moving from state 1 to state 2, it is isentropic, not it is actually compressing, and that compression is non-isentropic compression. So first thing first, we have to find the non-isentropic compression from the non-isentropic from the isentropic equation. We have to find the temperature, which means like T2 S, which actually is isentropic, by T1 would be equal to T2 by P1 gamma minus 1 divided by gamma. So that's what actually when we are talking about the condition which is isentropic, and we are using the equation of the ideal gas. Gamma for over here for the helium, for the monotropic, the gamma value is 1.67. So from here we can find the value of T2, which come up as 116.16 degree Rankine. Moving to state 4, which is exit of the turbine. So we have got the efficiency of the turbine given. So that means like the process is again non-isentropic. So we will be using non-isentropic anyway formula, but first we have to find the isentropic temperature over here. So isentropic T4 by T3, T4S by T3 would be equal to P4 by P3 gamma minus 1 by gamma, and we can find the temperature, which is TS4. Using the non-ideal formula or non-isentropic formula, which is the efficiency, non-isentropic efficiency would be equal to H3 minus H4 divided by H3 minus H4S for the turbine. And obviously for the compressor, it will be vice versa. So that would be equal to Cp T3 minus T4 divided by Cp T3 minus T4 as so make sure like this formula does not hold for or does not equal to this formula unless and until you prove like it is actually Cp cancel out in each one, as the formula itself is valid only in terms of enthalpy, not in terms of temperature. So if you're writing directly like gamma is equal to efficiency is equal to T3 minus T4 divided by T3 minus T4S. So this is a little bit wrong in my sense. Like you have to know, like in this formula, when the Cp cancel out, then that efficiency is equal to this formula. Moving to the temperature now. So we have got the efficiency given, turbine efficiency, which is actually around 80%. Now going to the compressor efficiency. So compressor efficiency is H2S minus H1 divided by H2 minus H1, and similarly you can find the temperature T2. Now once you have got a temperature T2 and T4, so you have already solved this topping cycle. So now we would be moving towards the bottoming cycle. Although you can find you can put the value in Cp delta T to find the enthalpy, but later on, like if we want to have this value, we'll find it anyway. Moving towards the Rankine cycle. So Rankine cycle, we have got different condition given. So at state 5, the condition is saturated. So having that at a pressure of 1200 psi, so at we can find the temperature, but definitely we do not need it. So at a pressure of 1200 psi, I can find the enthalpy H5 from the steam table, which will be enthalpy of the saturated liquid. So enthalpy HF at 1200 psi would be the enthalpy at state 5. Now moving to state 6. So we have got a pressure of 1200 psi and a temperature of 800 degree Fahrenheit. We have already in the pressure table, which is 1200 psi anyway. So looking at the correspondingly temperature, saturation temperature, so we would know like the saturation temperature is way less than 800 degree Fahrenheit. So obviously we are looking for the superheated steam table. So moving to a superheated steam table at 1200 psi and 800 degree Fahrenheit, we can find the enthalpy of superheated steam. Now moving towards the state 7, which is when we are exiting from the turbine, expanding the from the turbine. So once when we are expanding from the turbine, we are expanding to a quality which is 0.9. So at 1 psi, at quality of 0.9, you can find the enthalpy, and which would be equal to HF plus X HFG. So that would be X would be 0.9, HF from the steam table and HFG from steam table as well. Now going towards the enthalpy, state number 7, we have already got it. Step number 8, which is the saturated liquid at 1 psi. So we can find the saturated liquid at 1 psi, which would be enthalpy at 1 psi. Now moving to state number 9. So state number 9 would be the pump work. So we have already done many of the example uh, by finding the value of enthalpy using the pump work. So H9 would be approximately equal to H8 plus V8 delta P, and we can find the value of H9 from here. Now, we would need the value of H10 at state 10 and state 11, as well as we would be needing the change in enthalpy or the for the mass flow rate of the water as well. Um, so going towards the table at 60 degree Fahrenheit and 90 degree Fahrenheit, we would be finding the enthalpy at state 10 and state 11. But make sure this is what we call it as the approximate value at state 10 and state 11. It is because if I'm looking at the temperature, which is 60 degree Fahrenheit, and I'm assuming like the water would be actually going into the condenser from outside pond or from the pool, or so that would mean like the outside pressure would be 180 m. So that having said that, at 180 m 60 degree Fahrenheit, the liquid would be subcool. Again, similarly, at 180 m and a temperature of 90 degree Fahrenheit, it will be still in subcool region. So that mean like for the for these value, you have to go to a subcool steam table, or what we call it as a um, compressed table. So going to a compressed table or subcooled table, you can have a pressure of 180 m, 60 degree Fahrenheit, and you can find the enthalpy at that state. But that would be a little bit, still I'm saying like that would be approximately quite near to the value of 28.08. So this is not as useful like going towards the compressed table and finding the value. So it would be roughly equal to this one. But that's what actually you have to know, that it is the value which would be approximately equal to the value of this one. Now, the as we have already defined every enthalpy in the in the schematic diagram or the combined cycle, it is now we are not able to just putting the value and getting the answer. So that first thing is mass flow rate of the steam and cooling water. So if I'm looking at this control volume, which is the condenser, so I can relate mass flow rate of the steam over here from 7 to 8. We will be flowing the steam and obviously moving outside as a liquid. And also, if I'm looking at uh, this direction, which is actually from 10 to 11, then I would be having mass flow rate of a cooling water. Also, if I'm looking at this control volume, which is the HRB, the recovery boiler, uh, so from this end, I would be having mass of the gas, and then moving from 4 to 1, I would be having gas uh, exchanging its heat towards the water and to form the steam. And from this end, I would be having mass of the steam multiplied by the enthalpy, which is actually moving from 9 to 5. So these are the two control volume conditions. So if I'm looking at the mass of the steam, so mass of the steam would be much more easily find from this control volume, as in this control volume I have got the mass of the gas already available. The only unknown is actually mass of the steam. But if I'm looking at this one, so in this equation or in this control volume, mass of the steam is also missing and mass of the cooling water is also missing. So the first thing first, you have to find you have to solve the question using mass of the gas and mass of the steam, and then we will proceed further. So mass of the steam would multiply by enthalpy change in the steam HRB, which was moving from, let's say, I said like 9 to 5, uh, from the liquid feedwater liquid to saturated steam. Uh, that would be equal to the enthalpy change in from 4 to 1. So from 4 to 1, I've already said, like, if you want to find the enthalpy, you can simply put up in this equation, which is the equation in the ideal gas. So enthalpy change will be Cp delta T over here. Um, so we can find this enthalpy, or in other words, I can equate mass of the steam multiplied by enthalpy change would be equal to mass of the gas multiplied by the enthalpy change. I've said, like, Cp value would be equal to 5 by 2 R value for the helium. So I can find the value of Cp, which is 1.24 B2 per pound degree Rankine. Putting all these value in this equation, you can find the mass of the steam. Once you have find the mass of the steam, you have to go to the another control volume system, which is the condenser, and mass of the cooling water multiplied by the change in the enthalpy in a condenser would be equal to mass of the steam and change in enthalpy of the steam in a condenser. Uh, Equating them, finding the value of the uh, mass of the cooling water, which come up as mass flow rate of the cooling water, which come up as 1.63 into 10 to the power 7 pound per hour. Sorry for the other thing. These are the mass flow rate rather than mass itself, as there would be pound per hour in every case. Now the net power would be the total net power would be the power developed by the gas turbine and power developed by the steam turbine. So just putting them, like, work of the gas turbine would be equal to work W from the turbine minus compressor work. So we have already got the enthalpy changes, or the temperature at least. Putting the value, you can find the work done of the gas turbine. While the similar case would be for the steam cycle, putting the value of the um, enthalpies, and you can find the work done of the gas turbine, steam turbine, sorry. So once you have already got the work done and you can find the heat input, just put the value in the efficiency formula and you can find the thermal efficiency of the combined cycle using helium as a topping cycle, helium gas cycle as a topping cycle, and Rankine as a bottoming cycle. So the efficiency come up as 32.4%. I hope you understand this question. If you still have got any of if you people have got any of the question, you can ask me on a Google Classroom. Also, if there is anything, you can arrange a meeting in my office, and I would be able to help you out. Thank you very much. Have a nice day.